we will come back. So, this del square V del x square is equal to L C del square V del t square, this is equation 8, right. So, similarly, this is you will do it, I will not do it for you, you will do it, I have done it for you here only. Similarly, you can show that delta square I del x square is equal to L C delta square I delta t square. I mean, other two equations are there also you take the similar way, you take the derivative and you try to establish this one. So, this one is del square V del x square is equal to L C del square V del t square. Here also del square I del x square is equal to L C del square I del t square. Other two equations are there, similar way you take the derivative and put it, right. So, equation 8 and 9 you are known as transmission line wave equation. That means that this is the voltage, this is your for the voltage and this is for the equation 9 is for the current, right. Therefore, this they can be expressed as this equation 8 can be expressed as del square V del x square is equal to 1 upon gamma square del square V delta t square, and this equation can be written as del square I del x square is equal to 1 upon gamma square del square I del t square. This is equation 11, that is where gamma is equal to 1 upon root over L C meter per second, right. So, gamma we have defined at 1 upon root over L C. So, this way we can write this equation, right. Now, here gamma actually represent the velocity of the voltage and current wave, that is propagation, velocity of voltage and current propagation along the line, this is the gamma, right, in the positive direction. Dimension of L and C is same as Henry per meter and Farad per meter respectively, right. So, it can be shown that equation 8 can be satisfied by V f is equal to, that means in equation 8 means this one, look this one, this equation, equation 8. It can be shown that I am not going to the solution of this one, but we will make it in different way for understandable, right. So, can be shown that one is V f is equal to V 1, it is x minus V t, that is your 13, another is V b is equal to V t x plus V t, that is 14. While V f is equal to your forward travelling wave, that is a incident wave, you know that forward travelling wave, and V b is backward travelling wave, that is reflected wave. So, forward travelling wave is incident wave and backward travelling wave is after reflection it will come back. So, it is called backward travelling wave, right. And therefore, the general solution of equation 8, I mean this one, this equation general solution of equation 8, right, can be expressed as V x t is equal to V a plus V b, right. This way we define, one is your forward incident wave, forward travelling wave plus your what you call the backward travelling wave, right. So, this thing. So, this way you define. So, V x t it has the solution as one is V f, another is plus V b. So, this is equation say 15, right. That means V f is equal to your V 1 x minus V t and V b is equal to V 2 x plus V t. So, substitute here. If you do so, so it is V x t is equal to V 1 x minus V t plus V 2 x plus V t. This is equation 16. Now, that is the value of a voltage wave at a given time t and location x along the line is the sum of forward and backward travelling waves. If you know this expression of these two, you can easily find it out. Of course, the actual shape of each component is defined by the initial and boundary conditions of a given problem. You have to know the initial boundary conditions, right. That is the terminal condition, sending end, receiving end, right. For example, the relationship between the travelling voltage and current waves can be expressed as that forward wave, right. V f can be written as Z c into I p, you know Z c is the characteristic or surge impedance. V f should be equal to Z c into I f, and V b the backward one should be minus your Z c into I b, because it is reflected back, right. So, it will be V b will be minus Z c into I b. This is equation 18, right, where Z c is the surge or characteristic impedance of the line. Next is, that means we know that Z c is equal to root over L by C, that is L c to the power half. This is equation 19. Therefore, Vf is equal to If into Zc, therefore, If is equal to Vf upon Zc. This is equation 20, and this one IB, this is IB, this is actually this one actually it is IB. I am writing on a separate page. This is actually IB, right. IB will be minus Vb upon Zc, because Vb is equal to minus IB Zc. So, IB is equal to minus Vb by Zc. This is equation 21. Hence, the general solution of equation 9 same as before. The equation 9 we can write Ix t is equal to If plus Ib. I mean this equation, just hold on, this equation, equation 9, right. So, we can write, we can same as before, we are writing no for V is equal to If plus Ib. Similarly, I we can write Ix t is equal to If plus Ib. So, if you substitute this If and Ib here, it will be 1 upon Zc Vf minus Vb, right. So, this is the expression of I. Therefore, Ix t will be 1 upon Zc. So, Vf is V1 x minus your Vt, x minus Vt, and your Vb is equal to your x2 plus V2 x plus Vt. This is equation 23. Or Zc we know root over L by C. So, it is 1 upon Zc, therefore, Ix t will be C upon L to the power half V1 x minus Vt minus V2 x plus Vt. This is equation 24, right. Now, take something. The velocity of propagation of any electromagnetic disturbance in air is equal to the speed of the light. This you know, that is about 3 into 10 to the power 5 kilometer per second or 3 into 10 to the power 8 meter per second. That means to travel a distance of 2500 kilometers, say, an electric wave requires 1 upon 120 second, which is equal to the half period of the 60 Hz AC frequency. So, you can imagine how far it is moving with your velocity of propagation of any electromagnetic disturbance in air is equal to the speed of the light. That means, if for example, if a line is 2500 kilometer long, it will take just 1 upon 120 second, right, which is equal to the half period of the 60 Hz AC frequency, right. So, you can imagine how fast it is, right. So, as stated before, the velocity of surge propagation along the line can be V is equal to 1 upon root over L C, that is your meter per second. Since inductance of a single phase overhead line, this velocity V and voltage V should not be confused, right, it should not be confused. So, there should not be V also I am using, but there should not be any confusion, right. So, V is equal to 1 upon root over L C empty meter per second. So, since inductance of a single phase overhead line conductor assuming 0 ground resistivity, you know this expression from your inductance chapter, L is equal to 2 into 10 to the minus 7 ln 2h upon r Henry per meter. This is 26, and similarly the capacitor is C is equal to 1 upon 18 into 10 to the 9. I mean all this epsilon 0 after consideration of epsilon 0, approximately 18 into 10 to the 9 1 upon ln 1 upon 18 into 10 to the 9 ln 2h upon r farad per meter. This is equation 2. So, h is the height of the conductor above the ground in meter, and r is the radius of the conductor in meter, right. Therefore, this surge velocity in a single phase overhead line, it is V is equal to root over velocity 1 upon root over L C. So, substitute those values L and C values, right, and it was a reciprocal, no, everything I have taken to the power half, then overall to the power minus 1, because it is reciprocal, right. So, it is coming around 3 into 10 to the power 8 meter per second. So, therefore, surge velocity is same as that of the light, right. That means, you can imagine that traveling waves velocity. So, if the surge velocity in a 3 phase overhead line is calculated, if you try to calculate for a 3 phase line, you will find it is same as this value, right. So, furthermore, the surge velocity is independent of the conductor size and spacing between the conductors, because here this is a direct calculation 3 into 10 to the power 8 meter per second. So, it is neither the function of conductor size and spacing. So, it is the independent of the conductor size and spacing between the conductors, right. So, Similarly, the surge velocity in cables can be expressed as I mean, if it is a cable, it will be V upon V is equal to 1 over root over L C. Only thing is that it will be 3 into 10 to the power V I root over K meter per second, because the dielectric constant for cable will come here, right. So, in this case K is the dielectric constant of the cable insulation. This you can try also. You put the expression of L and expression of C of cable and put it, that one extra term will come, that is root K. So, that is, it varies between 2.5 to 4. For example, if you take it is 4, K is equal to 4. So, root K will be 2, right. The surge velocity in a cable can be found 1.5 into 10 to the power 8 meter per second, because it is to your 3 by 2 is 1.5. In other words, the surge velocity in cable is half the one in an overhead line conductors, if you value of K is 4. So, in this case also, in 121 by 122nd, the surge travels 1250 kilometers in a cable, as compared to the overhead transmission line, it was 2500 kilometer I showed you, but in the case of cable it will travel 1250 kilometers, right. This is due to dielectric surge power input to an energy storage. So, you consider the same 2 wire line shown in figure 2, I have already showed you. When switch S is closed, a surge voltage and surge current wave of magnitudes V and I respectively, this you know, travel toward the open end of the line at a velocity of, I mean, receiving end side for the timing, you assume it is open end, right. So, from sending end to receiving end, it is moving with a velocity V meter per second. Therefore, the surge power input to the line can be expressed as P is equal to V into I watts. This is equation 28. Now, since the receiving end of the line is open circuited, so line is open circuit, and we have assumed the line is lossless, right. So, energy input per second is equal to the energy stored per second, right. As the lines is lossless, so whatever input it is going, so it will be energy stored per second, right. So, if it is so, the energy stored in turn equal to the sum of the electrostatic and electromagnetic energy stored, right. So, that means the electrostatic component is determined by the voltage and capacitance per unit length. If you know that, this is Ws is equal to half Cv square, this is equation 29, this is electrostatic one, and for electromagnetic component is it can be determined the current and inductance per unit length, we know that Wm is equal to half Li square. Since the two components of energy storage are equal, right, both are equal, the total energy content stored per unit length will be W should be equal to Ws plus Wm, because both are equal, right, and we are considering it is a lossless, right. So, that means if both are equal, so W is equal to Ws plus Wm. So, we can write either W is equal to 2 Ws or is equal to 2 Wm. This is equation 32. Now, W is equal to, both are equal, it is half Cv square is equal to half Li square. That means, we can write that W is equal to your half Cv square half Li square, right. If it is so, you can find out that your surge impedance, right. Therefore, the surge power can be expressed in terms of energy content and surge velocity. That means, surge power P is equal to W into V, that is P is equal to your W is P is equal to, that is your what you call Li square your by root over L C is equal to I square Z C, right. I mean, from here also you can easily find out, right. P is equal to W, finally it will become Li square upon root over L C. So, it is actually I square Z C. Otherwise, from I square Z C you can from I square Z C you can calculate this one, right. You can just put this one and this expression automatically will get it. If you want, you start P is equal to I square Z C, right, and Z C component you know, and I square also you know, substitute every this thing I square Z C. If you substitute here all I and Z in terms of your this thing, and you will get P is equal to W into V. So, it is actually I square Z C. So, this is your what you call your surge power, P is called the surge power, right. Or another thing is, other way you can write this is V square by Z C, because this one I is equal to V by Z C. So, it will be V square upon Z C square, one Z C in the denominator will be cancelled. Therefore, you can get it that P is equal to V square by ZC. So, this is equation 36, right. So, now it is interesting to note that for a given voltage level, the surge power is greater in cables than in overhead line conductors due to the smaller surge impedance of the cable. In the cable, the surge impedance is small, right. So, that is why the given voltage level, the surge impedance power is greater in cables, because your denominator is less, right, than in overhead line conductors, and due to the smaller surge impedance of the cable, right. Slowly and slowly we will go into the deep of it, but first you take a small example, right, one or two small example. Suppose assume this is example 1, assume that a surge voltage of 1000 kV is applied to an overhead line with its receiving end open, that means surge voltage 1000 kV applied, but receiving end of the line is open circuited. If the surge impedance of the line is 500 ohm, determine the following: total surge power in the line and B is the surge current in the line, right. So, this is a simple thing. This is a simple thing. This is solution. So, total surge power is P is equal to V square by ZC. So, 1 into 1000 square by 500 is megawatt. So, kV square by ohm. So, megawatt. So, it is 2000 megawatt, and B, that was surge current is I is equal to V upon ZC. So, V is given your 1000 kV. So, it is converted to the volt 10 to the power 6 volt, right, 1000 into 1000 divided by 500, 2000 ampere, that is 2 kilo ampere, right. Now, example, to repeat example, assuming a cable with surge impedance 50 ohm. Suppose if a cable having 50 ohm, then total surge power will be V square upon ZC. It will become, actually here it was 2000 megawatt, here it will become 10 times more, 20,000 megawatt, right. Similarly, I is equal to V by ZC, it is 1 into 10 to the power 6 by 50, that is 20,000 ampere, 20 kilo ampere. Here also it is 10 times more, here is 2 kilo ampere, here it is 20 kilo ampere, right. So, this is one or two small examples we took. Next, we will go to the your what you call that superposition of forward and backward travelling waves. Just hold on. Just hold on. Superposition of forward and backward travelling wave. So, first before explaining all this, first I will show you the look at the figure, right. So, this here this one, this is the forward propagation. These figures I have taken from a book, right. So, because then figures are symmetrical, it will be easy for you to understand. So, this is a forward propagation, this is voltage Vf, this is x is increasing, the x is increasing for this side, right, and this is forward propagation, this is If, the current, right. Shape may be your dimension different, but shape is remain same, values may be different, shape is remain same. Now, for backward propagation, it is moving this way, this way. So, backward propagation, this is Vb, right. So, and in the case of current, backward propagation, current is negative, right. So, it is Ib. So, it is backward propagation, but it is current, this is Vb and this is Ib, right. So, and now if you add both Va plus Vb, right. So, in that case this continuous line is Va plus Vb and dash line is your, this is your backward and other one is forward. If you add this, it will be Va plus Vb. Similarly, in the case of current, this is your this continuous line, it is Ia plus Ib, but this is your the dash line, this is backward propagation and this is forward propagation. So, this is your backward propagation voltage Vb is positive, but backward propagation current, it is your what you call, it is negative. Now, this is the superposition, right. Now, if it is so, now the superposition of forward and figure 3a shows forward travelling voltage and current waves. This is your figure A, B and figure C, right. This is figure A, figure B and figure C, right. So, in this case the travelling wave current wave, note that x is increasing to the right in the positive direction. I told you this way x is increasing, right, and as before according to the sign convention. Figure 3b shows backward travelling wave voltage and current wave. This is backward your propagation voltage wave and this is current wave, right. So, and figure 3 shows the superposition of both, right, this I showed you. So, forward and backward waves of voltage and current respectively. It can be shown that on the loss free transmission lines, the voltage and current waves have the same shape being related to each other by the characteristic impedance of the line, and travel is distorted, right. So, that we will see later that how things are happening, right. So, further when two waves meet, this is very interesting, they do not affect each other. Suppose in the same conductor, right, or cable, when one is going this way, another is going opposite direction, if they both the waves meet, they do not affect each other, but appear to pass through each other without any distortion. I mean, when both are moving, I mean, one is, if one is moving this way, another way moving this way, there will be no distortion actually. Without any distortion, they pass your what you call through each other without any distortion. This is very interesting, right. Now, next is the effect of line termination. Now, you see, assume that Vf and If and Vb and Ib are the instantaneous voltage and current of the forward and backward waves respectively at the point of discontinuity. Discontinuity mean at the end of the line. This is sometimes we call at the point of discontinuity, at the end of the line. Now, hence the instantaneous voltage and current at the point of discontinuity, that is at the end of the line, V is equal to Vf plus Vb and I is equal to If plus Ib. This we know actually, previously we have seen. So, this is equation 38 and this is equation 39, right. So, now we know that substitution of equation 20 and 21, right. So, we know that equation from equation 20 you know If is equal to Vf by Zc and Ib is equal to minus Vb by Zc, right. Therefore, this thing, that equation 20 and 21 you put here in 39, that means this equation. Here you put If is equal to Vf upon Zc from equation 20 and here you put Ib is equal to your minus your Vb by Zc, right, in this equation 39 you put it. I am not showing again equation 20 and 21, no need, understandable. If you do so, you will get I is equal to Vf upon Zc minus Vb upon Zc. This is equation 40. That means I into Zc is equal to Vf minus Vb. Next is you add equation 38 and 41. That means this equation 38, this is your V is equal to Vf plus Vb, and this equation 41, this one you add. If you do so, you will get V plus I Zc is equal to 2 Vf. Therefore, Vf will be half V plus I Zc. This is equation 43, right. Similarly, your subtract equation 41 from equation 38, you will get this one. I am not doing for you, it is understandable. You just from equation 38 you subtract equation 41 and just simplify, you will get Vb will be half of V minus I into Zc. This is equation 44, right. Then another thing is alternatively from equation 42, I mean from this equation 42 you can write V is equal to, I mean this equation 42 you can write V is equal to 2 Vf minus I Zc. That means this equation you can write that V is equal to 2 Vf minus I into Zc. This is equation 45. Now, you substituting equation 45 into equation 44, that means this V is equal to your 2 Vf minus this one, this V value 2 Vf minus I Zc you put in this equation 44, you put it here. If you do so, then you will get Vb is equal to Vf minus I into your Zc. This is equation your 46, right. Now, next is line termination in resistance. I mean it is not open circuited now. Now, assume that the receiving end line is terminated in a pure resistance, right. I mean you have a receiving end side, I mean it is something like this, you have a sending end I am just putting like this, the way long transmission line we make, right. You have this thing, and here it is terminated by a resistance, R, right. Here termination by resistance by R, and sending end side everything is there, source and other thing. So, assume that the receiving end line is terminated in a pure resistor, so that V is equal to IR. This is equation 47. Now, substitute equation 47 into equation 42. I have to consider case by case, right. So, substitute this one into equation 42. I mean, in this equation you substitute V is equal to IR. Here you substitute, because line is terminated at in the receiving end at resistance R. So, V is equal to IR, you substitute. If you substitute, then you will get I is equal to 2 upon R plus ZC into Vf. This is equation 48, right. Similarly, and from equation 47, this I you got 2 upon R plus ZC. So, this I value you put it here in 47. This I is equal to 2 upon R plus ZC into Vf. You put it here. If you do so, you will get V is equal to 2 R upon R plus ZC into Vf. This is equation 49, or from this equation only Vf is equal to R plus ZC upon 2 R into V. This is equation 50. Similarly, for Vb you will do it for all this, substituting equation 48 and 49 into equation 44, you will get Vb is equal to R minus ZC by R plus ZC into Vf. This is equation 51. This is the expression for Vb, right. So, just you do it yourself. I have done all these things I showed. So, just I have written also, just if you put it, you will get it there, right. So, the power transmitted to the termination point by the forward wave will be Vf square Zc. Zc is a characteristic impedance of the line. So, it will be Vf square upon Zc. This is equation 52, right. So, next is that whereas the power transmitted from the termination point by the backward wave, it will be Pb will be Vb square upon Zc. This is understandable, right. So, it is 53. Therefore, the power absorbed by the resistor R is V square by R, because across the resistance voltage is V. So, PR will be V square upon R. This is, and it is a lossless line, right. So, PR will be, I mean, along the, this is along the this thing line resistance not considered. So, PR will be V square by R. So, line is terminated at resistive value resistance R, right. So, this is equation 54. That means, PR is equal to Vf, V is equal to Vf plus Vb. So, Vf plus Vb whole square upon R. This is equation 55. Now, so that Pf is equal to, actually Pf will be equal to Pb plus PR, or should not be confused that Pf forward wave will be this thing. Do not write Pf plus Pb hurriedly, no. Pf will be Pb plus PR, because Pf is that from the common sense you can make out from your intuition that Pf actually is the forward wave. Something will be reflected back and some will go to the resistor. So, Pf will be Pb plus PR. How we got it? Equation 52 minus this thing, equation 52, subtract equation 53 from equation 52. Then you will get Pf minus Pb is equal to 1 upon Zc, Vf square minus Vb square is equal to 1 upon Zc. It is A plus B into A minus B formula. So, you can write Vf plus Vb into Vf minus Vb, right. Now, Vf minus Vb we have from equation 41. Equation 41 we have seen that Vf minus Vb is equal to I into Zc, right. So, Vf minus Vb you put I into Zc, and you know that V is equal to Vf plus Vb. So, Pf minus Pb will be V by Zc into I into Zc. So, Zc cancel, it will be V into I. So, Pf minus Pb will be V into I, that is nothing but V square by R, that is equal to PR. That is why I am writing, so that Pf is equal to Pb plus PR. Common sense is that wave forward wave is moving, and after that at the receiving end something will be transmitted to R, because it is not open circuited, and some will be reflected back. So, basically Pf will be Pb plus PR. So, how things have been done, it is shown. So, thank you very much. Welcome.